Hello everyone, my name is Abhishek Chandar, final year undergraduate student from SRM Institute of Science and Technology. And on behalf of our team comprising of myself and Surya Suresh, who is also a final year student from SRM Institute of Science and Technology, we are going to talk about the prediction of seasonal southwest monsoon rainfall over India using artificial intelligence. Before starting with the presentation, here is a brief overview of what we're going to cover. So initially, I'll be talking about the basics of Indian weather system, followed by the seasonal prediction of southwest monsoon rainfall. After that, I'll be covering the existing approaches to predict rainfall, and I'll also cover about what artificial intelligence is on a very high level. After that, Surya Suresh will talk about the technical modules that we have adopted in our methodology. Then he will also be covering the performance evaluation of the proposed model with other baseline models, after which the limitations and the future scope of our research work will be discussed. To begin with, I'd like to talk about the major weather systems of India. So when it comes to the Indian subcontinent, there are three major weather systems of India, namely Western disturbance, Southwest monsoon, and tropical cyclone. So Southwest monsoon rainfall usually occurs during the months of June, July, August, and September. Western disturbance brings rain to the northwestern parts of the Indian subcontinent, which originates from the Mediterranean region. And tropical cyclone occurs usually during the months of May to June and October to November. So considering the stability and the relatively less erratic nature of the southwest monsoon, we focus on the prediction of annual long-range southwest monsoon rainfall using artificial intelligence. These are the different methods to observe rainfall. So we've got gauge, radar, and satellite. As we can clearly see, all of these the different methods are of different spatio and temporal scales. So all the three methods are sort of judicially used to determine the all India rainfall, which is used for making various calculations when it comes to agriculture or when it also comes to power management, etc. So rainfall has been predicted since time immemorial. Folklores were one of the most earliest and primitive methods of rainfall prediction. So again, as the world witnessed the technological advancement, the rainfall patterns were extensively studied with a lot of scientific approach. So later came the climatology and persistence techniques, which makes a fundamental assumption that the conditions at the time of the forecast will not change. After that, there were different methods like statistical and parametric methods. So in statistical and parametric methods, instead of just considering the previous rainfall data, the various other parameters that could potentially influence the rainfall is also taken into consideration for making the prediction of the rainfall. Finally, the ultimate goal of predicting a rainfall is to build dynamical models which tries to simulate the entire world's weather conditions by conducting complex meteorological calculations and performing different calculations using various meteorological related formulas to predict rainfall. Finally, ensemble methods are also used by a lot of researchers where different models are being used and the output of different methods, different models are taken into consideration, and the average of those different models are given as the final output. With our AI approach, we focus specifically on the parametric methods, since our approach will be using the global oceanic parameters for predicting the southwest rainfall. So let us delve into the three major aspects of the southwest monsoon rainfall. So here we have the interannual variation of monsoon rainfall from 1901 to 2015. So clearly in the x-axis, we've got the years from 1905 to 2015, and the y-axis has the percentage departure from LPA. So what that means is that the mean that we have here is 870 millimeters, and the standard deviation, which is represented by sigma, is 84.3 millimeters. So this is the percentage of deviation from the mean that we are able to see here, and the 10% mark above the mean and the below and below the mean represents the outliers, which are usually considered as extremely good monsoons or extremely poor monsoons. So we've got a good number of extremely good monsoons as well as deficit years. So this sort of gives a bird's eye view on the how the monsoon rainfall has been over right from 1905 to 2015. Secondly, we've got the climatology data for the daily rainfall, which gives just a visualization of the 2002 year and the 1994 year, because 2002 is considered to be one of the deficit monsoon years, and 1994 is one of those years that had extremely good rainfall. So this is just a visualization to understand how the trend works over the June, July, August, September. And finally, we've also got the climatology data, which is the average of the past 100 years of data. So to just use it as a benchmark and compare the deficit days as well as the extremely good monsoon. Finally, we've got the spatial rainfall image. So this particular visualization helps to sort of understand how the rainfall has been distributed over the Indian subcontinent. So we can see as the color becomes red, the intensity of the rainfall has increased. So the northeastern parts of India as well as the Western Ghats usually get a really good amount of rainfall when compared to the other parts of the country. So we have got a lot of previously existing machine learning and statistical approaches for predicting the rainfall. For example, we've got ARIMA and K nearest neighbors and different machine learning approaches. But this particular research in predicting the rainfall still exists, because after a point, statistical models and machine learning models do not perform really well, because, for example, statistical models work especially well with stationary data, and stationary data are those which can be represented by a single mathematical function. So in case if we want to extend the trend of that particular data, if we know what that mathematical function is, we'll be able to continue the trend and make the predictions. But when it comes to rainfall data, it is a lot more complex, and it cannot be represented with a single mathematical function clearly. So this is the reason why different methods such as deep learning is being experimented currently in order to predict the rainfall. So IMD currently employs a two-stage forecasting approach. So the first stage of the forecast is issued in the month of mid-April, and the second stage forecast is being conducted by the second week of June. So with IMD's latest approach, they are using two machine learning models, namely Ensemble Multiple Linear Regression and Project Pursuit Regression. So this is the basic outline or the flow chart as to how their statistical ensemble forecasting system works. So of course, they are one of the few researchers who are considering the global oceanic parameters for predicting the rainfall. So these global oceanic parameters that they are considering are fed into all possible EMR and PPR models, and out of the best performing models of both EMR as well as PPR, the average of the result is taken and the final forecast is being given. So this is how they currently work. And this is the visual representation of the spatial domain from which different global oceanic parameters have been obtained. So these are for a long period of time, these particular parameters have been scientifically proven to influence the Indian subcontinent, the rainfall in the Indian subcontinent. So the different parameters that they have considered are North Atlantic sea surface anomaly, Indian Ocean sea surface anomaly, East Asia surface pressure, El Nino 3.4 index, and North Atlantic surface pressure. So we are also considering Indian Ocean dipole, which we have mentioned here. This particular parameter is something that the previous researchers have not used, and this is one of our novelty in our approach, apart from the deep learning model that we are proposing. To talk about the comparison of existing algorithms, a lot of previous research attempts have used the previous rainfall data in most of the cases. Some have used hourly data, some have used daily data, and with respect to the methodology, a lot of different statistical and machine learning models have been implemented. Rajivan et al. Is one paper which has used global oceanic parameters for prediction of the Southwest Monsoon Rainfall in India. The inferences that we found from the previous research work is that the prediction of rainfall was conducted for a restricted demography, or was conducted in predicting short-term rainfall data. But the number of research attempts that takes the entire Indian subcontinent into consideration and giving annual rainfall data is very handful, and not a lot of researchers have delved deep into it. Because although annual rainfall data is a gross number, it holds a lot of importance in the overall management of the power management and various other agricultural operations. So before moving on to the AI methodology that we are proposing, I'd like to briefly talk about what artificial intelligence is and how it works. So on a high level, artificial intelligence is basically a mathematical model which is inspired by the human brain that can be used to discover useful patterns in data. So for example, the way in which it works is that the input that we have, for example, in our case, is the global oceanic parameters that we're considering for predicting the rainfall, which is fed into the neural network or the deep learning model, and it gets processed through the nodes, and it is then given as an output, which again in our case is the predicted rainfall value. So in this particular Venn diagram that we are seeing right now, deep learning is an intersection of both machine learning as well as artificial intelligence. But deep learning will always be a subset of artificial intelligence. The next obvious question is why deep learning? Because there are a lot of statistical and machine learning approaches out there. But why deep learning is the next obvious question. So there are two main reasons. So the first reason is the elimination of the need for feature engineering. So what that means is that deep learning approaches do not necessarily need to be specified with the parameters that we're going to use for predictions explicitly. So even in the case where we are not really sure about which global oceanic parameters or any other parameters that could potentially influence the rainfall values, the data can be fed into the model, and the performance of the deep learning model will not suffer on a significant level when compared to machine learning or a statistical approach. And the second advantage is the ability to deliver high quality predictions every time. So once the deep learning model is trained, unlike a machine learning model, unless and until the training data is changed for some reason, the quality of the model, which means the result that we get, is not going to vary much. So this is something that's important, because this helps to have a particular deep learning model which proves to be more solid when compared to a machine learning or a statistical model again. So after this, Surya Kiran will be talking about the AI methodology that we are proposing, and he will also be discussing about the performance evaluation, followed by the limitations, and he will conclude.
Thank you, Abhishek, for giving us insight on the Southwest Monsoon Rainfall and explaining about the AI models and different deep learning models. Well, I would be talking about our approach in this particular research problem, which we are tackling. And when it comes to our approach, we have divided our approach into 3 different technical modules, where the first module is identifying the key parameters for Southwest Monsoon Rainfall. The issues addressed in this particular module would be the error due to the irrelevant features in the data set for rainfall prediction, and we'll try to reduce the error by finding the key parameters for the Indian Southwest monsoon. And the second module in this research area would be identifying the deep learning algorithm which will be used to predict rainfall. And we'll try to select a deep learning model in order to reduce the error and increase the accuracy of the model. So that will be our key goal in this particular module. And the third module would be the performance evaluation of our proposed module, proposed model, and we'll compare and contrast our proposed model with the baseline models, which are the predictions available from the Indian Meteorological Department. So going ahead with module 1, identifying the key parameters. The data which we have used, we had to take the raw data and we have to convert it into monthly format by applying data pre-processing techniques. Then the global oceanic parameters were identified, which actually affect the Indian Southwest monsoon rainfall. And these are the parameters which are used in our model. In this, our novelty is using Indian Ocean Dipole, which is considered in the months January, February, and March. And the spatial domain is taken as 2 grids and subtracted both the values of this, both the values obtained from these grids are subtracted. The significance of correlation with Southwest monsoon is given in the last column, and you can see that all the parameters have high significance with our with the Indian rainfall, and hence we are using these parameters with the months and the spatial domain mentioned in the table. So this is the correlation heat map of the parameters which we have used, and you can see the first column is basically the correlation coefficient with the different parameters and the rainfall. And East Asia pressure has the highest positive correlation, whereas El Nino has a negative correlation, and it is also the highest in negative. Apart from that, we can see that most of the parameters have a decent correlation values, and they are not very correlated with each other. Second is module 2. We are actually identifying the deep learning model which we are using to predict rainfall, and we have finalized a deep learning model which is known as multi-layer perceptron. To explain what a multi-layer perceptron is, there is a image out here which actually shows how the multi-layer perceptron looks like. The input layers is number of parameters we are giving as input, and the output layer is the rainfall value, the amount of rainfall in millimeters which we are predicting. In between all of these, there are multiple hidden layers, and these are the layers which are between the input layer and the output layer. Each circle out here is called as a node, and the nodes we'll be showing in the next slide. All these parameters are known as hyperparameters, and in the next slide we'll be showing what are the hyperparameters which we have used. The model configuration which we have used for the multi-layer perceptron model is basically having a batch size of 6. Number of epochs is 1500, and number of nodes in the first hidden layer is 26, and number of nodes in the second hidden layer is 13. So what do you mean by epoch is basically when a model is said to have completed one epoch, the model has gone through the entire training data set once. So that is basically completing one epoch. And similarly, our model has gone through the entire training data set for 1500 times. So that is 1500 epochs. And batch size is number of data points which the model has to see before it updates its weights. So for each node. So our model has a batch size of 6. That means it goes through 6 data points before it updates its weights. So using these hyperparameters, we have got a model error of 5% of LPA. This is the architecture diagram which we are using, where we collect the data first, and the feature engineering is done on which parameters to be used. And we have finalized these 6 parameters with the spatial domain mentioned over here. And then next, what we do is we scale the data to between 0 and 1, because the deep learning models are very sensitive to data which are high value. So we scale the data to between 0 and 1, and then we build a feature matrix out of it. We feed the feature matrix inside the proposed model, which is multi-layer perceptron, and get the intermediary results. Once we get the results, what we do is we do a inverse min-max scalar on the data and obtain the final monsoon rainfall value. So this is the IMD's latest attempt on predicting the rainfall for the past years till 2019. You can see here that they have got a correlation coefficient of 0.58 with an RMSE of 65 mm. So here the error which they have got is almost plus or minus 65. And you can see that their prediction in 2019 seems to be around 800, but the actual value was somewhere around 960 or 970. Now we can proceed to our model, which we have proposed. This is the prediction of our proposed model, and here we got a correlation coefficient of 0.78, which is highly correlated to the rainfall, actual rainfall value, and the RMSE which we have got is around 56 mm. The green labels are the actual rainfall value, and the red ones are the predicted values. And you can see that for 2019 we got somewhere around 920, and the actual value was 960. So our error margin is a bit less than what IMD has proposed. So in conclusion, we actually show that the prediction for the year 2020 is 918 as per our model, and the actual value, which was the rainfall value, it was 981 mm. The prediction for 2021 will be made in April, because we are using parameters which comprises of the months March as well. So we have to wait till April. The limitations of our model are, so the historical data points which are available are not enough for parameters such as El Nino, because El Nino data we could find only from 1958, and we couldn't go back beyond 1958. So we, if El Nino value for years before 1958 were available, so it would have been useful. Then the better detection of outlier cases is one of the limitation in our case, because in 2002 it was a very deficit rainfall year, and even our model was not able to predict the deficit rainfall, and this is one of the limitations in our approach, which can be added as a future scope, because we can work on the model to get more data points and probably try to predict the outlier cases as well. And the experiment on ensemble techniques using deep learning algorithms and different machine learning algorithms are yet to be conducted. So this can be considered as one of our future scopes, which we are yet to perform. So these are the references which we have used in our approach, in our research. And thank you everyone for paying attention. On behalf of Abhishek and myself, we thank Dr. M.S. Narayanan and Dr. Fatimal for their guidance. And thanks to IWSS organizers for this wonderful opportunity.